University of British Columbia. Okay, we'll speak about the geometry and arithmetic of banana. So it's tropical part, but nano-manifolds, I even have no idea what is it. Jim, please.
I'll explain what a banana nanomanifold is. I mean, part of the terminology actually does make sense, but a lot of it is because it's fun to say, banana nanomanifold. Okay, so I'm interested, and yeah, the geometry, enumerative geometry, and arithmetic, and actual geography as well. So if we're talking about tropical things, we're interested also in geography. So the tropics is part of geography. So the definition here, let me start off with an easy definition for everybody. Just a smooth projective variety over C for me is a dimension D Calabi-Yau, So of course we want the canonical. So I'm making this projective. So already I'm just going to discuss for the moment projective Calabi-Yaus. So we want the canonical to be trivial. And since I'm over C, I can talk about the Hodge numbers. Is it smooth? If it's smooth, yeah, it's smooth. If the k0th Hodge numbers sort of look like the usual Betti numbers of a sphere, so unless k equals 0 or D, so somewhat of a purist definition of a Calabi-Yau. And let me say some things that probably most people know, but it's kind of fun to remind ourselves, what the situation is. So of course, if D is equal to 1, these are elliptic curves. And there's, of course, there's a moduli space of elliptic curves, but topologically, there's only one topological type. D equals 2, because I've put this sort of strongish relation on the Hodge numbers. This does not include abelian surfaces, but of course this includes K3 surfaces. And once again, the projective K3 surfaces have a whole interesting moduli story, but topologically, again, there's just one topological type. So for D equals 3, which is what I'm primarily interested in here, these are, for lack of a better name, Calabi-Yau threefolds, CY3s. And unlike this, what happens in dimension 1 or 2, this is much larger. This is somewhere greater than 500 million topological types. And let me just say, probably, because we don't even technically know that is true, what I just said. We have constructions of these things, so most famously as complete intersections in toric varieties. You can sort of classify the conditions that you get a Calabi-Yau, and this leads to combinatorially an enormous number of Calabi-Yau threefolds, over 500 million constructions of that type. Now, technically, we don't know that all those constructions lead to topologically different Calabi-Yau threefolds, but that's nobody sat down to try and systematically prove statements like that, but that's probably true. And moreover, we don't actually know, this estimate is coming from one class of constructions. There's a lot of constructions out there. We don't even know if the number of topologically distinct types is finite or infinite. So there's already sort of an interesting problem of just thinking about the topology, possible topologies of Calabi-Yau threefolds. the idea that it's finite, but kind of an enormous number like 500 million is sort of more interesting than if it actually turns out to be infinite. Miles Reed has this quote, which is, 500 million is so much more impressive than just a mere infinity, which I've always thought was kind of a funny way to put it. So one of the aspects sort of that we might be interested in Calabi-Yau threefolds is the very just simplest, which is like topological classification. And one sort of piece of the topology is are the Betti numbers, which in this case are encoded in the Hodge numbers themselves. And so we can say a Calabi-Yau threefold has two interesting Hodge numbers. So, several of the Hodge numbers are either 0 or 1 by the Calabi-Yau condition and the various conditions I've imposed. The two, and then others are determined by symmetry. The two that determine the interesting ones are H11 of X, which is the number of, so they each, and H11 and H21, and they each have geometric significance, right? So H11, you can think of as the number of independent Kahler classes, and H21 is the number of independent complex deformations. So this is sort of the infinitesimal picture that famously gets switched in mirror symmetry, the Kahler deformations and complex deformations. And so these two numbers determine those two things. So in particular, if this number is 0, so there's no complex deformations, we call such a thing rigid. So let me throw that as a definition. A C by 3 X is rigid if the number of complex deformations is 0, so it just doesn't have any complex deformations, is 0. It's kind of fixed as an isolated point in its moduli. Okay, so I'm interested in sort of three aspects of Calabi-Yau threefolds, which I'm going to put on the board in a second. This kind of question of topology, or at least the coarsest form of topology, so geography, which numbers of these guys are possible. I'm also interested in enumerative geometry, which is actually how I came to the subject. The other things are a little bit newer. And in this case where X is rigid, these tend to be defined over rational numbers or integers, in which case there's actually arithmetic to be done. We can sort of study solutions mod P and whatnot. So those are the three aspects, and let me write them on the board how I want to write on the board how I'd like to study Calabi-Yau threefolds. So three aspects of Calabi-Yau threefolds that let's just sort of think about all three simultaneously, and that are sort of interesting.
So Jim, if one wants to make parallel with D equal 1 case, it should be rigid. It's like elliptic curves with complex multiplication. I mean, it's no.
Well, kind of. I mean, they always have elliptic curves. Always have deformations, right? So there's not a pure analogy like this.
No. But if you require the endomorphism group is something like z plus z square root of minus 2, so you cannot deform it within this class. It's kind of rigid. So
yeah, that's right. There is an analogy of sorts. Yeah, that's right. I mean, you could also an analogy would be for K3 surfaces would be this is terrible jargon, but they're called supersingular or singular K3 surfaces, meaning that the Picard lattice is as big as it's allowed to be, and then if you're looking at deformations preserving the Picard lattice, those would be rigid. So there's an analog in K3s as well. So three aspects. Geography, I'm going to put it, all right, let me see if I can get this three things here: enumerative geometry, and arithmetic. All right, let's hope this fits. So, okay, the geography question asks what values of these numbers H21 and H11 can occur, right? So obviously if the number of topological types is finite, then this sort of collection of which values can occur are finite. And in particular, we can ask for what are the smallest values? What are the smallest values? So you could measure smallest by the sum. So this is like saying, what's the smallest total? It's equivalent to asking what the smallest total dimension of the homology of a Calabi-Yau threefold. How small can it be? So in fact, this was studied in the physics literature a little bit fairly recently. There's been an interest in these Calabi-Yau threefolds with small numbers, and Candelas with some co-authors have written all constructions where the sum of these two numbers is less than 20. I'm going to define a nano-manifold, so nano meaning small, to be where the sum of these two is less than or equal to 4. So this is about as small as shows up on these lists. So a nano-manifold will be when it's less than or equal to 4. Maybe I should write that. So nano-manifold means that the sum of H21 plus H11 is less than or equal to 4. Okay, so the enumerative geometry of a Calabi-Yau threefold, by this, what do I mean? I really mean computing. So I'm mostly interested in computations here, computing the, well, we could call it string, or we could call it Gromov-Witten or Donaldson-Thomas partition function. So if you study the partition function in topological string theory, or the partition function, the generating function for Gromov-Witten invariance, or the generating function for DT invariance, these all contain, these are all functions which contain the same sort of set of information, the information of all the Donaldson-Thomas invariants or all the Gromov-Witten invariants. And so it has all the enumerative geometry, but what we're really interested in here are like the automorphic properties of these partition functions. So, so these are generating functions. So let me just write what I was going to put in the board here. Generating functions for enumerative invariance. Generating, that's what these partition functions are. Generating functions of enumerative invariance, like Gromov-Witten or Donaldson-Thomas, numerative invariance. And specifically what I'm interested in is modular properties, understand modular properties of these functions. So, in various contexts, it's understood that these partition functions will satisfy some differential equations and whatnot. In some more specific settings, which I'm going to talk about, they will actually be various kinds of modular forms on the nose. And that's sort of very interesting when that happens, that these are modular forms, gives you sort of other ways to think about those enumerative geometry invariants. So that's one of the main interests. And the third interest is arithmetic. So what is this here? And this is something that my interest is more newly come to, but rigid CY3s. So remember, those are those are guys with no deformations. These tend to be defined over Q, and as such, they are modular. So now here, modular. This is the same sense in which elliptic curves defined over Q are modular. So what that means is that counting points over finite fields, one sort of down-to-earth way to say this is counting points over finite fields, FQ, gives rise to a weight 4 modular form. So, you know, the Wiles-Taylor theorem for elliptic curves defined over Q says that if you count if you count solutions over a finite field, so you count number of points mod some number, these are going to be very closely related to the Fourier coefficients of a modular form of weight 2 in that case. And the analog for Calabi-Yau threefolds, which is also true, is that it's weight 4 modular forms. And some of the bigger stuff here is that the middle cohomology, in both cases, the middle cohomology is 2-dimensional. So what's special about rigid is the middle cohomology is now 2-dimensional, which means that, and if this thing is defined over Q, then I get a Galois action of the absolute Galois group, Q bar over Q, on this middle cohomology, a tall cohomology, and that gives me a Galois representation. And those Galois representations, there's this whole long story about how they give rise to modular forms. But concretely, you know, the Fourier coefficients of those modular forms you can get just by doing arithmetic. So it's kind of this nice story where arithmetic leads to a weight 4 modular form. And of course, this is a really pretty different way that a modular form can arise from enumerative geometry, right? Sort of, these are quite different types of stories. This is arithmetic giving you a modular form. This is like Gromov-Witten theory of some sort giving you a modular form. So, okay, so that we're interested in those three things. Okay, so today, what I would like to do is I'd like to construct some rigid Calabi-Yau threefolds that are interesting from all 3 points of view. They're going to be nano-manifolds. They're going to be very small. They are going to be Calabi-Yau threefolds of banana type. I'll tell you what that means. But being a banana manifold means actually gives us a tool to compute a big part of the Donaldson-Thomas partition function. So we'll actually be able to compute the partition function and study its modular properties. And again, because it's rigid, we can try and do it with arithmetic and get some modular forms there. So the point of today is to construct some examples that are interesting from all 3 points of view. And show you these Calabi-Yau threefolds. I think it's also just kind of a nice construction, but it's constructing Calabi-Yau threefolds which have these interesting properties from all points of view. Okay. Okay, so today I'm going to construct xn. So these are going to be, so n, there's going to be 4 examples, and n is going to be at this number 5, 6, 8, or 9. So again, interesting from all 3 points of view. So one, they are, new, haven't been discovered before, rigid nanomanifolds, rigid nanomanifolds. So H21 and H11 are 0, 4. So these are, again, they're rigid and they've got Picard number 4. They've got sort of 4 independent curve classes. As I mentioned before, they are of banana type. And I will tell you what that is. So can compute the Donaldson-Thomas or Gromov-Witten partition function, DT partition function for 3 of the 4 classes. So can't do a complete computation of the partition function of Calabi-Yau threefold. Maybe I should remind people, or if you don't already know it, is that there's no Calabi-Yau threefold for which we know, even conjecturally, the complete partition function. So that's kind of a big open problem of what are these partition functions. So, you know, these ones where we can compute this big part of it, and for various reasons think they have some really nice properties. These are maybe candidates for manifolds that maybe one should be able to compute the full partition function of. And in fact, the modularity, I guess I can give a little spoiler to the Gromov-Witten potentials, the genus G Gromov-Witten potential. So once you've got the DT potential, you can compute the Gromov-Witten potential. Again, now this is going to depend on 3 curve variables. These are modular forms. They're Siegel modular forms, genus 2 Siegel modular forms. So they're like functions on the moduli space of genus 2 curves but really sections of a line bundle of weight 2G minus 2. And there's this n floating around, so there's kind of a notion of a level to these Siegel modular forms of level n. Okay, so we got these small manifolds. We can compute the Gromov-Witten partition function. We see that they've actually got not only sort of modularity on the nodes, they're really genus 2 Siegel modular forms. And
excuse me, what's G?
Yeah,
G.
G is the genus. So the Gromov-Witten,
okay.
Yeah, so the Gromov-Witten potentials, you can, you know, Z would be put them all together, but you can sort of look at them genus by genus. So now each genus by genus, this is going to be a generating function for the genus G Gromov-Witten invariance. And you're going to get a different Siegel modular form for each genus, and they'll have weight. It's like that. So it's like saying, I mean, there's sort of a mirror symmetry implication here, which is you should be thinking of the genus G Gromov-Witten potentials as being sections of line bundles over the mirror guy. And this is very suggestive that the mirror manifold should be a genus 2 curve, because these Siegel modular forms are basically sections of line bundles over the moduli space of genus 2 curves. Or maybe it's better to think of it as abelian varieties of abelian surfaces, right? So genus 2 curves and abelian and principally polarized abelian surfaces are very similar.
Yeah, but for genus 2 curves, there was kind of a bunch of papers by Aruk, Tsarkov, and many people. So they, of course, they just prove some kind of homological mirror symmetry, not the computation of Gromov-Witten, but will it be?
Yeah, and what they do is kind of local rather than global. But yes, it is very relevant to the story, I think, which is we're going to see pieces of geometry. In fact, the bananas from the title and the T-shirt, the bananas appear in that you know, Abu Zayed, Aru, Karsakov paper. And indeed, it's that mirror symmetry where you see that genus 2 curve showing up on the mirror. It's very similar geometry. Yeah. So that is related. Yeah. Okay. So
So here, assume that here the x-ns, this 4x-ns, it's a Calabi-Yau 3.
Yeah, Calabi-Yau threefolds. Yeah.
But you said the genus curves, so I'm a bit of confused. So are you meaning that the mirror dual will be a curve, or which has a genus?
Well, so the mirror dual, so it's funny because these rigid guys do not have mirrors in a traditional sense, right? Because, a mirror Calabi-Yau threefold would have Hodge numbers 4, 0, but of course you can't have a Calabi-Yau threefold with 0 as a Picard number. So these don't have mirrors in a traditional sense. So it's sort of a long story about how to make sense for mirror symmetry for rigid Calabi-Yau threefolds. You can think of it as in the boundary of a family, like where this is a conifold transition. You can try and think about it homologically, where like that mirror Hodge diamond, which doesn't actually exist for a Calabi-Yau threefold, might be a orthogonal summand in the derived category of some larger variety, right? So that there's been ways of making sense of mirror symmetry that way. I think it's fair to say I don't completely understand mirror symmetry. Well, no one does, but I don't even have the beginnings of understanding in these cases. But this is sort of a clue as to when you make sense of mirror symmetry, you should see on whatever the mirror is, you should see in its moduli a genus 2 curve. So this is some sort of clue.
Okay.
In fact, it's maybe it's even worth saying it. I said genus, it should be like the moduli of genus 2 curves, but I think it's actually better to think of it as the moduli of abelian surfaces, because this level business, it's really like abelian surfaces with a different polarization kind of condition. So it's maybe even better not to think of them as genus 2 curves, but instead think about them as abelian surfaces.
Okay, thank you. I'm looking forward to see how it's
good.
related.
Okay. And so finally, just the third thing was the arithmetic, and that we actually can compute. I'm sort of spoiling all the punchlines, but why not? We can compute the weight 4 form, compute the weight 4 modular form associated to the arithmetic by actually going in and counting points. And it ends up being the unique, cusp form for the modular group gamma 0 n, where n is this n, which is also going to show up in the geometry. So it's that n. Okay, so that's kind of cool that shows up as well. And these modular forms are pretty different. These involve more variables. This is just sort of traditional modular forms in the arithmetic. And of course, it would be extremely interesting to find some connection between the modular forms showing from arithmetic and the modular forms showing up from enumerative geometry. And there's speculation about this in the physics literature, but I think it's fair to say nobody really has a clue what's actually going on. Okay. So so I want to, this is primarily about constructing Calabi-Yau threefolds, right? So I want to construct these guys for you. I think we can, it's not too crazy. So I think we can explain it, but I need to warm up for the construction. Warm up is, I'd like to describe the general banana manifold. So I said these are some very special banana manifolds. I'm going to describe kind of the generic banana manifold, which is something I started thinking about many years ago. Maybe you even heard me give talks on it, but let me just refine it. So warm up, describe the general banana manifold. So how do you do this? So let's call it X-ban. So let's start with a surface which hopefully is, a favorite among everybody. All geometers should love these generic rational elliptic surface. So this is B, the generic hypersurface. of degree 3, 1, right? So I'm sitting inside of P2. I've got 3 variables. Inside of P1, I've got 2 variables. The equation cutting this out should be linear in these variables and cubic in these variables. And so, well, if I project onto the P2, right, then generically, I'm fixing that. Generically, I have a linear equation. And so generically, there's only one point. So projection onto P2 realizes that S is a blow up at 9 points of P2, right? So that's the projection onto P2, right? The 9 points where this is, of course, a pencil of cubics, and this is the 9 base points of the pencil. And then projection the other direction. This is an elliptic fibration, right? Because this is, of course, a family of cubic curves inside of P2. Those are elliptic curves. So you have a family of elliptic curves, and as long as this thing is generic, we're going to get 12 nodal fibers. So some of the singular fibers will be nodal with 12 nodal fibers. So let's draw a picture of that. And this is a surface, and I want to make a Calabi-Yau threefold out of this. I'm going to let me move that in a second. Okay, so that's a fairly easy slide. So everybody remembers that. So what do I have? I have my S to P1. This is an elliptic surface. So over my P1, I have a family of elliptic curves. There are sections given by the exceptional divisors of the blowup, and I'm going to get 12 nodal fibers, maybe N1, let me call it, through N12. Okay, so this is my picture of that surface. And now I can take a fiber product of S with itself over the P1. Okay, so let's do S cross over P1 with S. So here's my P1, here's S, here's another copy of S. So, you know, generically, the fiber of this is now a threefold. The fiber over a generic point is just a product of an elliptic curve with itself, E cross E. And then I've got some singular fibers, which look like the product of 2 nodal fibers like that. And if you remember back to your topology, when is a fiber product smooth? It's smooth at the locus where one or the other maps are not singular, the map itself being singular. So where is this map singular? This map is singular exactly at these points. And so at this node cross node, I get a singularity, and that's easy to sort of see. That's a conifold singularity. So this guy has 12 conifold singularities. And so if I want to make a Calabi-Yau threefold from conifold singularity, I want to use a small resolution. So I don't want to blow up those points. That won't give me something Calabi-Yau, but I want to replace that point with a P1. And of course, the problem with conifold resolutions is there's two different ways to do it. And in general, so you can always do that locally, you have 2 choices. But the problem of showing that a global, that some singular threefold has a global projective resolution, it actually can be kind of subtle. In this case, there's something very simple we can do, which is we can blow up the diagonal, right? So inside of here, I have a Weil divisor, which is just the diagonal, right? So that's a Weil divisor, a P of S cross over P1 of S. Now, as you know from your basic algebraic geometry class, normally you should think of when you blow up a divisor, nothing happens because, you know, it's principal locally defined by one equation, so the blow up doesn't do anything. But of course, the whole point is that this is not a Cartier divisor, this is a Weil divisor. And at the singular points, it requires two equations to describe it. And so when you blow up this divisor, it doesn't do anything away from the singularities because there that divisor is Cartier and blowing up does nothing. But exactly at the singularities, it gives us conifold resolution. So this guy is a Calabi-Yau threefold, a CY3. And it's, you know, it's Hodge numbers are as follows. So the H21 is 8. So these are the deformations. And in fact, it's exactly the deformations of the S. So in this construction, the only thing that you can deform is the rational elliptic surface itself. And that has, you can figure it out, that has 8 complex deformations. And H11, the Picard number is 20. So these are not nano in any sense. These are quite big. But like I said, this is the warm-up. And let's see, the fibers, it's kind of worth saying what the fibers are. We did it already. So if this is, yeah, did I ever give this a name? I didn't. So let's give the blow-up a name. So the fibers of X band. So this is fibered by abelian surfaces in general. The generic fiber is just E cross E. So not only abelian surfaces, but abelian surfaces of Picard rank 3, right? So E cross E is a very non-generic abelian surface. And the singular fibers so let me say F singular. Well, let me tell you, so if I look at a nodal fiber of an abelian of an elliptic surface and I remove the singular point, I get a copy of C star. In fact, that's the group scheme part. And so in this fiber product, at least the group scheme part is a product of C star cross C star. And so you can think of the singular fiber as like a compactification of this. And it's compactifying C star cross C star by a banana configuration of curves, which I'm going to tell you in a second. So this is where the bananas come from, banana configuration of curves. Okay. Let me, before I move the board, let me give you a chance to grab that, but I want people to get a picture in their head of what this singular fiber looks like. It gets because it gets, you know, a little bit harder to think about. So what is the banana configuration? So this is 3 rational curves. So CI, so these are P1s with normal bundle. So they're all P1s. They intersect, let me do it this way, intersect CJ in 2 points, P and Q, and their normal bundles are, these are all -1, -1 curves. So this is, you know, some Calabi-Yau 3 geometry. These curves are kind of as nice as you can get. So I sort of picture it like this. Here are my 3 P1s. They meet at points P and Q. So it's like a bunch of bananas, right? This is the banana, but it's also joined at this point here. And each of these P1s have normal bundle, O -1, O -1. And in fact, the local geometry depiction is a little misleading, is this is 3 curves meeting in 3 space locally. And this is like the coordinates, it's like the coordinate axes in C3 is formally locally how these meet. So there's actually kind of toric. In fact, it's a non-normal toric surface. So F singular you can think of the normalization of that surface as being P2 blown up as 3 points. So, you know, if you like sort of toric looking pictures, this would be, I guess, the momentum polytope of P2 blown up at 3 points, and the boundary divisors would be 6 P1s, but because this thing is non-normal, that they get glued together. So if this is, you know, P, Q, P, Q, P, Q, you take this guy and you glue this boundary divisor, that boundary divisor, that to that, that to that, and then those boundary divisors give you this banana configuration. Okay, so this is this structure. This is like a fibration. I like to think of people have studied Calabi-Yau threefolds with like K3 fibrations. Okay, and you can maybe study, for example, the fiber-wise enumerative invariance in terms of sort of singular fibers and local invariance and things like this. So I like to think of this sort of banana story is now we're looking at Calabi-Yau threefolds that are fibered in abelian surfaces, but these kind of particular ones, especially abelian surfaces, where the degenerate fibers are these very, very special, formally, locally toric things, okay? So they're non-normal toric, these toric degenerations. But the point is that this actually allows us to compute the fiber-wise Donaldson-Thomas partition function. So we can compute the dt partition function for fiber-wise curves. So in this case, in this banana case, this banana manifold, there's 3 curves here, these 3 bananas, and actually those generate the curve classes of the fibers. So you get a partition function that depends on 3 curve variables, and you can actually compute this for fiber curves using sort of a mixture of toric and motific methods for curve classes, fiber curve classes. Okay. And I'm not, I could write the partition function for this, but I want to get to the new manifolds and I'll write the partition function for that. How are we doing on time? Okay. Getting there. Okay.
So
does this hopefully
for the fibers you use a Hilbert scheme for the surface? What's the building block for this DT? Just
yeah, that's right. The Hilbert schemes. So you showed that the Hilbert schemes of curves, so they're living in the fibers, and you can use the fact that DT invariants have this kind of motivic property show that the smooth fibers don't contribute. So you first show that all the contributions come from these singular fibers, and now you're using the fact that in a formal neighborhood of the singular fibers, so it's important that it's not just the singular fiber, but a little formal neighborhood, that thing is still actually toric. And now you can do torus localization, and you can do a very elaborate, long, complicated vertex calculation to actually get the partition function. So it boils down to a vertex calculation. So the slogan I like here is this is a compact Calabi-Yau threefold that's very far from being toric, but it's actually close enough to being toric when you're studying these fiberized classes because you can reduce everything to these pieces of it which are formally toric. So this guy, even though he's compact, behaves a little bit like a toric Calabi-Yau threefold, and moreover, the vertex calculation is actually something you can do, and that's actually a very sort of long and interesting story. It's related to geometric engineering, but that's kind of why this works, and that's why you get interesting answers. Is this vertex calculation? So topological vertex. So yeah, you know, there's this long story in enumerative geometry about doing torus localization to compute things, and the basic building block there is the topological vertex. And this is a geometry where even though we're not toric, we get to use toric methods. So that's kind of one thing I like. Okay. So how do we get these banana nanomanifolds? What we do is we start with, instead of starting with a generic rational elliptic surface, we start with a modular elliptic surface. So, okay, so these are the banana nano manifolds. So Sn over P1, again, so n is going to be in 5, 6, 8, or 9. So be a rational elliptic surface with, instead of having 12 singular fibers of type I1 in Kahler's classification, this would have 4 singular fibers of type IK1, IK2, IK3, IK4, where these Ks I'm going to record with a 4 tuple, which I'm going to call theta n. So the 4 tuple, and there's just 4 choices of this. So theta 5 is 1, 1, 5, 5. Theta 6 is 1, 2, 3, 6. Theta 8 is 2, 2, 2, 4, 4. Notice these numbers all add up to 12. And theta 9 is 3, 3, 3, 3. And let me just draw, let me do one, I'll keep a running example, which will be the n equals 6. So S6 to P1 now looks like this. Maybe should have to be wider. So I've got a singular fiber of type I1, which is just a single nodal P1. I've got a singular fiber of type I2, which is 2, it's a cycle of P1s. And then I3 is a triangle of P1s. And then finally a hexagon of P1s. That's the 1, 2, 3, 6. And why do I call this this is a modular elliptic surface? Because the Mordell-Weil group of sections, so these are elliptic surfaces I can study their group of sections. The Mordell-Weil group of sections, is a group Gn of order n. That's the n. So this has actually a cyclic group of order 6, and moreover Sn. So one way to think about this rational elliptic surface is it's a compactification of the universal elliptic curve. Is a compactification. Oh God! All right, I better hurry. Of the universal elliptic curve over the moduli of elliptic curves equipped with an embedding, of this finite group Gn into the elliptic curve. Right, so you could think of, for instance, here the group is Z mod 6. So you could think of this as this P1 is the moduli space of elliptic curves with a fixed 6 torsion point. Okay, so then that gives me this surface. So this is modular in that sense. Okay. Right. So one more thing to say to give the construction, and then I'll give the punchlines here. So we want to construct out of that guy. Good. So in particular, I have Gn acts on this whole thing, and it acts fiberwise because it's a subgroup, so it acts by translation fiber-wise. And because it's a subgroup of an elliptic curve, it's going to be free everywhere potentially, except for maybe at the singular points. And so I can let S prime n be, I'm going to take the quotient by Gn. Now that'll give me a singular surface, but I can take its minimal resolution. All right. So let me give you, in this case, let's just understand what this is. If I take the quotient of this guy by S6, what's going to happen? Well, on that, it's going to be smooth everywhere on the regular fibers, but on these singular fibers, what happens? Well, this one, the group will spin everything and it'll fix this point. So this will end up being like a Z mod 6 orbifold point. And then over here, the group will exchange this, but it'll have stabilizers of Z mod 3 there. And so I'm going to get a Z mod 3 orbifold point. So this singular guy actually is a elliptic surface with 4 singular fibers where they all look like nodal fibers, except that they've got potentially orbifold points. And so when I take the minimal resolution to get S prime of n, an orbifold point of Z mod 6 in the resolution, I get 5 curves. And so those 5 curves, along with the proper transform of that node, now give me a hexagon. And this guy's going to give me 2 curves, so I'm going to get a triangle. And over here, I'm going to get a bigon, and this was already non-singular, so that just stays. In fact, I see that what I get is a copy of that surface, but after a base change. So in fact, it ends up being, again, this surface is related to the fact that if I take an elliptic curve modulo, say, a 6 torsion point, then there's a canonical 6 torsion point on that quotient given by the Weil pairing. Okay, so I get a new surface, and this is the one that I'm going to take a fiber product of. So now I've got Sn cross over P1 with Sn prime. So what's this picture? I've got S6. I've got S6 prime. And this is something, so now what do the singular fibers look like? So here I've got a hexagon paired with this thing. I've got a two-gon paired with a triangle, and I've got my triangle paired with this bigon, and this thing paired with a hexagon. And this has 4n conifold points. And it still has an action of Gn on each of these factors. But now something kind of magic is if I look at the diagonal inside of Gn cross Gn, this acts freely. Just by analyzing what the fixed points are on each side here. And so let me define, leave that picture there. Let's define Xn to be, so I'm going to blow up along a certain Cartier divisor, which maybe I won't, which is actually pretty tricky to construct, but maybe I won't say what it is specifically right now. Sorry, along a certain Weil divisor. And I'm going to divide by this diagonal action of Gn. And the theorem is that this guy, Xn, well, so a big part of the theorem is that this blow-up procedure actually gives me a conifold resolution. So this is a smooth CY3 with, as promised, H21 is 0 and H11 is 4. And moreover, when I take the quotient, so when I blow up these conifold points and I take the quotient, the thing that remains is actually a banana fiber. So this has, instead of 12 banana fibers like the old thing, this has 4 banana fibers. It has 4 banana fibers. And the 4 curve classes, the 4 divisor classes, so it's got Picard number 4, the 4 divisor classes are given by the class of the fiber. I'm going to give names to these because I'm going to tell you what the partition function is in a second. S is, you know, one of the surfaces crosses 0 section. I've got S prime, which is the other surface cross the 0 section. And there's a class which is related to this gamma, but this is basically the Poincare dual of the conifold curves. Poincare dual of the conifold curves, the ones that you got from the resolution. Okay, so now, ready for the big reveal here. So, okay, so I got 4 classes, and I'm going to compute I'm going to compute the Donaldson-Thomas partition function. Let's see, can everybody see that? So what is the Donaldson-Thomas partition function? It's a generating function for Donaldson-Thomas invariants. So Donaldson-Thomas invariants have a curve class beta and a Euler characteristic number n. So I sum over all n, and I'm not doing all beta, but I'm doing all curve classes which live on a fiber. So if I dot them with that fiber divisor, I get 0. And then I have 3 curve variables which are indexed by their degree with respect to the remaining 3 divisors. So this is a 4 variable function, and we get a very explicit formula for it, which is, you know, maybe not worth writing in real time, but worth taking a look at because it's actually got a very beautiful formula. So remember, this theta n was the list of the 4, you know, like in the case of n equals 6, this is a 4 tuple. This is 1, 2, 3, 6, for example. So I'm going to have 4 products, and each product is going to contain, this is like a product formula for the partition function. This kind of product formula is something we like in DT theory. We like it when things have product formulas like this because these exponents tell us a lot about the BPS states. This is sort of a nice formula to have it in, form to have it in. And you can see that the particular numerology of the singular fibers sort of manifests itself up in interesting ways in these variables. And that this coefficient up here, these things related to the BPS states, are actually really nice things. They are the coefficients of the equivariant elliptic genus of C2. So this is a particular function that shows up in this subject, coming really from geometric engineering. So C2 is a Calabi-Yau surface. When you have a Calabi-Yau surface, you can compute its elliptic genus, and its elliptic genus will have modular properties. In order to define elliptic genus from something non-compact, you might need some equivariance, but of course so you have an equivariant elliptic genus. And here it is very explicitly. These coefficients are, you can also write it as the coefficients of a theta function. So so this is a ratio of these theta functions. I mean, so here it is completely explicitly. Here you can put it into your maple, generate these numbers, put these in, and get that completely. But the corollary, and I realize I'm out of time, so I will just say the corollary out loud, is that you can now, once you have the DT partition function, you can run the MNOP. Well, it's conjecture, but John Parton has proven it. So it's a theorem to get the Gromov-Witten partition function from which you can compute the genus G Gromov-Witten potentials. And, you know, I can actually, as I said in the punchline, since maybe I won't actually write it since I'm out of time, But the punchline is then the genus G, you can use this formula to compute the genus G Gromov-Witten invariants, and you can prove that they are Siegel modular forms for a very particular congruent subgroup called the paramodular group of the group of the arithmetic group associated to Siegel forms, so the symplectic group. So okay, so and then the other part that I maybe I won't write down, but is that you can, with that explicit elliptic the abelian surface vibration, you can actually now count points over finite fields. We have explicit equations for those guys because we have explicit equations for those elliptic surfaces. And so you can count points over finite fields and really compute those modular forms and get what I said, which is that the weight 4 modular form is the unique cusp form on gamma 0 n. All right, so I think I'll stop there. Thanks for your attention.
Thank you very much. It's really very exciting stuff. So are there any questions?
Yes, I do have a few questions. So
Okay.
on this partition function, and on the left-hand side, you have Q and Y being the variable.
There's the curve variables are the little q, big Q, and Y are the curve variables.
Yeah, there's the little q, and on the right-hand side, when you write that in terms of modular forms, you have a tau and a z. So I'm curious which one corresponding to which one.
Oh, okay. No, that's a good question. So there's two things going on here. So the Q, the little, yeah, this is worth, okay, can I put it, let me put it right here. Right. So the claim is that now if I go to FG, so now I've gotten rid of this variable that keeps track of Euler characteristics. So if I go over to Gromov-Witten, I've got a variable keeping track of genus. I can look at each genus, and this now only depends on little q, big Q, and Y. And now what are the variables? The genus 2, I have it in my notes here. The upper half, the Siegel upper half plane, right, is parameterized as matrices, right? Sort of symmetric matrices. So these are complex numbers, sigma, z, tau, and there's some analog upper half plane for these sorts of symmetric matrices. And capital Q, so it's really nice. It's exactly what you would hope for on those 2 pi I with a little factor of n in here. Little q is exponential of 2 pi I tau, and y is of 2 pi I z over n. So, this is up to maybe this factor of n. This is the usual sort of way you would go in between the Fourier variables and the Taylor variables at the origin. So these are kind of like the Taylor variables in the Taylor expansion at the origin, and these are the Fourier variables at the cusps. And same thing here, right? The tau and the z. So I guess, I mean, this formula here is independent. This is defining these guys. So there's yet more modularity here. The Jacobi form, and here the Q is e to the 2 pi I tau, the Y is e to the 2 pi I z. So it's basically the same thing. Yeah.
Okay, thank you very much. That's
yeah.
So for the power of a little q, and so that was the integer that was somehow let's see, on one part, yeah. So you are taking the summation with the n running through the integers, or for the Donaldson-Thomas invariance n back, yeah, that part.
Yeah.
And so I'm curious what the ET beta. Beta is a homology class, but n stands for the Donaldson-Thomas invariance of what?
Of my nano-banana manifold, right? So these are the Donaldson-Thomas invariance of a nanomanifold. And so what is that beta? That beta
That is
you
the
should think of it-
homology class. That's right.
Yeah, it's
But
a
the N
combination
here
of
stands for
N is Euler characteristic.
Euler
sorry.
characteristic. Okay,
Standard
thank you.
notation
Yeah,
for the DT.
Yeah, so these DT invariants involve if you want subschemes, ideal sheaves of subschemes. So a Hilbert scheme of curves, but whose Euler characteristic of the structure sheaf, right? So it involves subschemes, and N is the Euler characteristic of the subscheme. This
So
is
the
just
Euler
sort of
characteristic is N, little n, right?
it's little n. You should think of
Okay.
it. You should think of it as being related to the genus. It's like keeping track of genus, but because we're doing subschemes,
Yeah, I understand.
it's not really
Okay.
formally genus. But if it's really like a smooth curve, right, then the Euler characteristic is 1 minus g. So it's more natural on the DT side to keep track of Euler characteristic, but it's analogous to keeping track of genus. Yeah.
Mhm. Okay, I'll probably ask one more question for Yan to wait for a minute.
Sure.
So you said, but in the arithmetic sides, and you expect that this modular forms should be counting some rational points over finite field.
Yeah.
So do you have any say or some kind of a model what those varieties are, and so you can count the number of rational points over finite fields.
Yeah, I mean, so these banana manifolds, which I
Are
remember
defined over, you say, over rational
over
numbers?
Z. Yeah.
Okay,
So
I
of
see
course
you can
it's defined over
spread
Z.
that into an integer, some kind of integer.
So you can literally count over, but one way to think about this modular form is that this modular form associated to this x n, it has a Fourier series, right, which is a n q to the n, and it's got a property that if you look at the key, this is trace
of the Frobenius.
Yeah, Frobenius p acting on the, if you want the install cohomology of x and coefficients in QL bar. It's the trace of that guy for almost all p. There's some weird p, like when p divides n, this is not true, but it's enough to actually determine these are Hecke forms. It's enough to sort of know it on these primes. Yeah.
I see. So the variety is just the xn itself.
Yeah, that's right. That's right. It's very funny. So with a rigid variety, rigid Calabi-Yau threefold, you can sort of count things in two ways. You can count curves, or you can count points over finite fields, and you get modular forms in both cases. And it's sort of hard to see. This sort of feels, these guys counting these things, it feels very much sort of like counting sections. Sort of the way you count is you count sort of on each elliptic fiber, on each abelian surface fiber. So in some vague sense, you're counting sections, which is of course the part of the Donaldson-Thomas theory that we don't know how to do. I only know how to do fiber-wise things, right? So I don't know how to do it, although I have some guesses at what happens if you throw in like one section. I mean, there's another part of this story. One of the reasons I'm interested in these manifolds is they should be related to what are called CHL models in physics, which I studied a few years ago with Overdyk. And the least when you're degree 1 over the section, you should be getting the same things that we saw in the CHL model. So there's some argument for that. But so I think these are interesting guys to study the full DT theory of. But right now we can only do fiber-wise DT theory completely.
I see. So Thomas Hausel and Natelier, and they also did something mostly somehow related to the quivers. The one side is a complex geometric formulation of the Donaldson-Thomas invariants. The other side was just looking at counting the number of
character varieties, points on character
quiver variety.
Yeah.
And is this kind of similar to that, or in the same spirit, or something different?
Well, it's not unrelated, because you can turn that story, which is a beautiful story, into an understanding, in some sense, of Gopa-Krumov invariance of local curves. So there's two different ways you can get a Gromov-Witten invariance of a local curve. One way would be with sort of Malik-Toda's definition, which involves perverse sheaves of sort of one-dimensional sheaves on that thing. Or the other way would be with, computing Donaldson-Thomas invariance or PT invariance and going through the Gromov-Witten conjecture to relate them. And the relation between those two turns out to be exactly this sort of two sides of the Housel story for what do you call them, Hitcham systems, right? Where when you're doing the perverse filtration of the Hitcham system, that is precisely like doing the Malik-Toda theory for local curves. And when you're doing the counting points over finite fields of the character variety, what you're really getting at are the it's like doing the PT theory. It's like doing the motivic counts of the PT theory on that side. So it's not unrelated. It has to do with understanding the relationship between the Gromov-Witten invariants, which are basically these exponents, and the PT invariance, which is the whole thing. But the case where you're talking about is really understood for local curves, and this is far from local curves. Now, it's not quite as global as I make it seem, right? These are global compact Calabi-Yau threefolds, but as I was saying to Jan, in some sense, it does boil down to sort of a local calculation where locally everything's living at those bananas. So it's conceivable, actually I've thought about this, I haven't made progress, but it's conceivable that there's some quiver or maybe some enhanced quiver story that could give you the invariance of this banana configuration, and then maybe some back and forth, but on the other hand, this particular count for these rigid guys, this is a little bit more global. This is much more than just the banana curves. In fact, this doesn't even really care much about the banana curves. This is really about that family of elliptic curves is what we're really counting. The rational, one thing that's sort of true about when you do these rational counts is that it doesn't really care much about the rational parts, the rational curves. It really cares about more like the elliptic curves.
Okay, thank you very much. Very interesting talk. Now,
So
yeah, it's over for you.
For Hausel and others, it's two Calabi-Yau story, not three Calabi-Yau story. So I don't think you can really relate.
Well, no,
them. I think it's conceptually different because instead of -1 shifted symplectic structure like here and the perverse shift on the corresponding digit stack, you have in the two Calabi-Yau case, you have 0 shift. It's much more simple. There is no wall crossing. So
well, yeah, that's right. So in the Calabi-Yau 3 story, that's because, right, so the Calabi-Yau, the local curves that we have in mind are like O cross K. So that very quickly reduces down to a surface, right? So then you get the surface case. So if you study the sort of Gromov-Witten story for the local Calabi-Yau threefold, which is O, the total space O plus K, then the Malik-Toda sheaves, they all live, basically they all live in the K surface. They all live in that surface, and so then it does go down to a surface story, and then you're right. There's just
but it's different. I don't think it's story, but actually it's more or less understandable. So the same methods give the refined invariance as well, yeah? Or, no?
Unfortunately, Jan, no. I wish, and the problem is that the refined invariance will have contributions from the smooth fibers, from just like elliptic curve cross elliptic curve.
Yes.
And so I lose kind of control of that. I've tried for a long time to find some way to do it.
Okay.
So you can do a formal computation at the singular fibers, but I suspect what you get is not really giving you any information about the refined invariance of the global thing.
So you really need the theorem that everything localizes over singular fibers. That's a crucial part. Yeah, I have also a question. For any Calabi-Yau, the automorphism group of the DB Koch derived category of coherent sheaves, it's very large. It's like lattice. So then, if you consider generating functions of dt invariance as it should be as a function on I don't know, on the space of stability conditions, although we don't know any for compact, but just hypothetically. So then it should be kind of automorphic just by default because it's invariant. And I remember that, you know, when Nathalie Paquet mentioned this banana stuff long ago, it wasn't nana banana, it was just banana. And so I asked her whether this modularity can be derived in the end just from general principles, from the action of autoequivalences of DB Koch.
You know, so a slightly more down-to-earth version of, I think, what you're talking about. For example, there's work of Oberdijk and Shen, which show that if you have a Calabi-Yau threefold that with an elliptic fibration, and you fix a class in the base, and then what they do is they study derived automorphisms of the Calabi-Yau threefold that basically come from doing Fourier-Mukai transforms on the elliptic fibers. And of course, whenever it is a lot of work because, okay, so you get some derived automorphism, but now you have a numerative invariance associated to that sort of place. And if you want to relate it back to your good old fashioned, you know, DT invariance so that you get an actual relationship of your DT partition function, you have to do some wall crossing. So they do that. They do, you know, they do a derived equivalence and then they do wall crossing and they show that that derived equivalence gives rise to part of the modular properties of Jacobi forms. So this is part of the story that Calabi-Yau threefolds that are elliptically fibered, if you fix a class in the base and you sort of let the curved fiber run, you get a Jacobi modular form, and this is part of that. So these guys can fit a little bit of that. Like you have these two elliptic fibrations, you map to each of those surfaces. So you can do the derived automorphisms for Fourier-Mukai fiber-wise. Yes. And that should give you some of these. And then I think you can actually do more by doing on the abelian surface. You can now do Fourier-Mukai on the abelian surface. And so what I suspect is that you get you get roughly half of the automorphic properties this way. The other part should come from something more like holomorphic anomaly. It should come from something more that lives on the moduli space.
No, I understand better what you said about this P equal W. The difference is that indeed you have, I mean, in some sense it's similar to the Hitchin fibration. You have a generic fibration by abelian tori, abelian surfaces, but the total space in your story is not a I mean, it's not complex symplectic. So that's
right.
Yeah, so then it's it's a different type of P equal W. Okay. Yeah, all right. Good. Okay, more questions? Well, if there are no more questions, Jim, thanks again. Very interesting talk. And this is it for today.
All right.